Okay, it's 9:30, so let's get started. This is, I think, lecture 3, second lecture in chapter 2, and we got a couple more. And I don't know, there's a test coming up, probably, well, let's see. Let's see what the schedule looks like here. It's not a bad idea. 3210. Okay, so there's the schedule. I suspect the test will be on that day. Looks like we're staying pretty much on schedule so far. So that's September 22nd. It'll be probably around 25 questions. Some will be multiple, but right now most of it's multiple choice. Some of it's definitional, but a fair amount of it's going to be little problems. So you'll have to work through a given scenario and indicate A, B, C, D, whatever the correct answer. Yes, sir. Laura? Did you start the recording? Yes, I did. I think I did. Yeah, it's recording. But thank you. Thank you. You can't be too careful. Okay, so just, want to keep the schedule in mind. That first test on the 22nd. It will be through iLearn, and it'll be timed. It'll be the class period. You can come and sit in the class, or you can take it wherever you want to. It'll be open book, open notes. So right now, that's the information on the first test. Okay, let's get back to the presentation. I'm sorry, I can't hear you. No, there's no lecture. There's no lecture on test day. That's enough. we after an hour and 20-minute test, we've gotten our pound of flesh out of you for that day. So we'll let you go with that. So this is where we wound up last time, I believe. So we're on to the different modes of heat transfer we'll talk about. So we've got, I don't know if you're currently taking or have taken the heat transfer course, we have 3 basic different modes of heat transfer: conduction, radiation, and convection. And so we'll go through each one of those in some degree of detail here and talk about it. So conduction, transfer of energy from more energetic particles of a substance to less energetic particles due to interaction. So, the idea there is, say I've got, I don't know, that's not a very good mass. Let me say my cell phone is all heated up and I put it on a cold block of ice. I have actual contact between those hot molecules on the surface and the cold molecules on the surface of the other object. They're touching each other. And it's typically thought of as molecular vibration. So the hotter it is, the more it vibrates with different modes of vibration. When they come in contact with one another, some of that energy of vibration is transferred from the hot to the cold. So the hot one doesn't vibrate as much, so it cools down, and then the cold one that's in contact starts vibrating more, so that's a more energetic state, so that heats up. And then if you continue to, say, heat a surface like this, then those molecules, if it's a homogeneous material, like steels and, like materials, a lot of them have like a regular structure, atoms and bonds and all that stuff together. So this one up here starts vibrating, and then through the bonds and the contact, this one starts vibrating, and then this one and this one and this one and this one, and it slowly propagates through, okay? And how quickly it propagates through depends on the material. Copper, take a copper pan or a block of copper, put it on the stove, put your hand on the top of it, turn the burner on. You're going to be moving that hand pretty quick. The energy gets transmitted pretty quick through that copper. And that constant is the thermal conductivity. That's the number that we use to characterize how readily heat is transferred by conduction through an object. You could take a brick, on the other hand, and set it on that burner. You could turn on your electric burner or your gas oven, set that brick on there. And if it was a big block, so it didn't come around the edges, you could set your hand on there probably for quite a while before it got so hot you couldn't stand it. So it's just a difference in conductivity, how those molecules are free to vibrate and transmit that energy. And of course, conduction is also, it's a vector quantity. So if you're going to do a three-dimensional conduction, you have conduction in the X, the Y, and the Z. And conductivities don't have to be the same in all directions. There are certain materials that just based on how the molecules are linked together and line up and all that stuff may have a much higher conductivity in one direction than another. That may be selective. They may be engineered for that, to conduct heat this way, but not laterally, that sort of thing. So you get, mathematically, conduction becomes pretty complex. You get if you take a graduate level conduction class, it turns out to be a big mathematics class, Fourier series and all that sort of thing. When we start out in here, we do one-dimensional and pretty simple. And your heat transfer class, you'll get into some multi-dimensional stuff as well. Time rate of energy transferred by conduction is quantified by Fourier's law. Old Fourier, as we used to say, but the French call it Fourier. And we'll see the equation on the next page. But yeah, the classic example is heat transfer through a wall. It could be a floor, you know, from down below up above, or it could be a vertical wall. One temperature on one side, one temperature on the other. And that's kind of what we're depicting there. And those temperatures are surface temperatures. Okay, you got to be a little careful there. And the dashed line is just the control volume. Or I guess you could say control mass in that case, because you don't have any mass moving in and out. So that could be a control mass. It's just that section of the wall. And you see T1 is warm because it's at a higher level, and T2, it's cold outside. So if that's a homogeneous material, constant K and all that sort of thing, so then you get a linear temperature profile at steady state, okay? So, you know, you can also do a transient problem where you have to, you know, maybe the whole wall is cold and you set it, you turn on the heat, it comes up, and then, you know, the temperature profile comes up in the wall until it hits steady state, and then the Q is constant after you get to steady state conditions. Notice the area is perpendicular, would be that plane into and out of the screen, and X we're taking to be positive in, what is that? That's right? That direction, the right direction. And notice that the heat transfer is taken positive in the positive X direction, because we're going to have a little sign convention here in all this stuff in just a second. So, I don't know. Pretty straightforward from that point of view, I guess. Okay, so there's Fourier's law. So Q dot, so the dot means what? It's a rate. So that's like kilojoules per second, or it could be watts, could be in US units, it could be BTUs per minute, per hour, per second, you know, whatever time base you want. Okay, and then we got K. We'll talk about the minus sign in a minute. We got K, which is that conductivity. You just look that up in a table. You know, I emailed out some of the tables. You need to you need to look in the back of your thermo book. Just browse through there and look at all of those tables and just kind of see what they give you back there. But there's a table back there with thermal conductivities. There's all kinds of these properties that we're going to talk about. You probably got, I don't know, 100, 120 pages of tables back there in the back of your book. We'll get through In this course, well, we'll get through half of them, something like that. But you need to become familiar with those. A is the area normal to the heat transfer, normal to the x direction, perpendicular that x coordinate is going through. So that would be the YZ plane, a slice, x going this way, y and z. And then dt dx is just the temperature gradient in the x direction. Okay. Okay, so if the heat is flowing, let's see what we got. Do we have a good diagram? Well, yeah, we'll go on down here for a second. Okay, K is proportionality, thermal conductivity. We talked about that, just a property of the material. The minus sign is a consequence of energy transfer in the direction of decreasing temperature. Okay, so heat's going to flow what? From high temperature to low temperature, right? You can't, if it goes the other direction, it busts the second law, as we'll see. So, you can't do that. So if this is the positive x direction, say going to the left, and that's the temperature of decreasing, or the direction of decreasing temperature, then if you look at the dt, a T2 minus a T1 is always got to be negative, right? Because the temperature is going down. So you go further down, it's a lower temperature. T2 minus T1 is negative. The x coordinate, that's the positive x direction. So x2 minus x1 is always positive. So that dt dx is always negative in the direction of, if the heat flow is in the positive coordinate direction. So we have to introduce that minus sign. So that counteracts the dt always being negative. And so you see that down on the bottom. dt dx is T2 minus T1 over L, but L is x2 minus x1. But the denominator is positive because we select the coordinate direction that way. And then because we want positive heat transfer in that direction, we have to introduce the minus sign. Okay. So think about that. So then for this problem that we showed up here, where we have L and T1 and T2 and all of that, then this last equation on the bottom right, Q dot X, the rate of heat transfer in the X direction, minus Ka, T2, the outside wall temperature, which is cold, minus T1, the inside wall temperature, which is warm, divided by L, the thickness of the wall. And that gives your conduction heat transfer rate. So, questions? All right, so we'll roll on. Radiation. Okay, so this is when you go down to the beach and lay out there and get your nice suntan. You're experiencing radiation from the sun. Thermal radiation is energy transported by, and there's two different theories in physics. You probably remember this. There's the wave theory and there's the photon theory. And different aspects of radiation are better characterized by one or the other of these, depending on what it is that you're wanting to describe. So physicists use both. But unlike conduction, there's no intervening medium. It can take place in a vacuum. Obviously, if the sun is going to get energy to us from way out there in space, there's not much in between until you get to the Earth's atmosphere. So it can be transmitted through a vacuum. Time rate of energy transfer by radiation is quantified by the Stefan-Boltzmann law and different variations of that depending on the problem that you're working on. Okay, so let's take a look at an example here. So we've got this flat surface laying down there kind of on the bottom of that diagram, and it's losing heat to the surroundings. You see Q dot C coming off of that thing. I'm not sure why it's not Q dot R, but anyway, they put a C on it, so it's Q dot C. So that's the net radiant exchange between that hemispherical surface, which is at temperature Ts, and the flat surface, which is at temperature B, TB. Okay, so you've got two temperatures up there, and that E, little small, that's a lowercase epsilon, is the emissivity, and that's a surface property of that slab that's laying down there. Okay, and again, emissivities can become complicated. They can actually be directional in nature, but at this level, it's just a constant that applies to the surface. And it defines how efficiently that surface can radiate energy. Okay, and in heat transfer and radiation, an ideal radiator, one that can radiate the maximum, can emit the maximum energy from its surface as a function of temperature, is called a black body radiator. Okay, and so if epsilon is 1, then you have a black body radiator and you are emitting the maximum theoretical possible radiation from the surface at its temperature. Now, as temperature goes up, you can emit more, that sort of thing. But that's what epsilon is. It is the efficiency with which that surface emits radiant energy. So the closer to 1, the larger the heat transfer is going to be, the furthest from 1, and it's a 0 to 1 scale. You know, at 0 you would get nothing, and I don't know if I doubt there's anything that's really 0, but not that I'm aware of, but I haven't looked for it either. Okay, area, surface area that's involved in radiation. Yes, sir.
Specific to radiation?
Yes, yes, yes. And when you do the heat transfer, there's three properties that have to equal 1. There's emissivity, absorptivity, and transmissivity. So, you know, that deals with all of the radiation. Say if radiation comes in, let's say radiation can be emitted, absorbed, or passed through in those. So anyway, you'll get into that in your heat transfer course. Okay, now the other well, here, let's get the equation. So the net energy transferred in the direction of the arrow is quantified by epsilon. How effectively does this surface radiate energy? Sigma, that's the Stefan-Boltzmann constant. That's just a constant. It's got some units on it. And area is the area on that slab that is participating in the radiation. And then you've got, it's a 4th power relationship. So you take TB to the 4th minus TS to the 4th. Now that has to be absolute temperature. Don't be putting in degrees C or don't be putting in degrees F. You're going to get a big wrong answer. Got to be absolute. When in doubt in engineering, you're better to use absolute. There may be a few cases you get into trouble, but by and large, especially in thermo, when in doubt, use absolute, and it will most likely work out for you. Now, the other thing, which is not in here, which you get into in the radiation course, which is pretty complicated, is a view factor. And they don't even mention it in the book. But a view factor is, it talks about, say, if you want the radiation from that slab surface, if you want the net radiation, then you have to be concerned with all of the different surfaces that slab can see, because it can radiate to anything it can see. Well, see, they conveniently put this hemisphere over it. So the view factor, you call it from like F slab to F surroundings, is 1, because that's all the top of that slab that's doing the radiation, that's all it can see, right? Because that whole thing is laying over the top of it. What if that thing was only half? It was, instead of being 180 degrees, was only 90 degrees. then part of what that slab would see would be that dome, and the other part of what that would see would be whatever's on the other side. And now whatever's on the other side is going to have a different temperature most likely. So see, it gets complicated. You have to do a net exchange between that slab and everything that it sees. So there is a view factor here, but this is conveniently contrived so that the view factor is 1 and they don't have to talk about it, because view factors get complicated because you have to do the three-dimensional geometric integrals in order to figure out what percentage of what one thing sees is something else. So you do some of that. There's charts that we use in heat transfer for different standard geometries, like you got 2 planes that are offset a little bit. You can go in and calculate some parameters and pull a view factor off the chart. If you take a graduate course, then you get to go out there, and a lot of times you have to numerically integrate in order to figure out, or you can do these Monte Carlo simulations where you fire a gun 1,000,000 times and it calculates the trajectory and figures out what percentage of the time that trajectory hit a particular object. I mean, it's pretty cool stuff, really. It's also kind of a pain in the rear. Anyway, okay, so his definitions here: A is the area of the smaller surface, the slab that we're talking about. Epsilon is the surface property called emissivity, and sigma is the Stefan-Boltzmann constant. Okay, so that's 2 of the 3. So we got conduction, 2 solid objects conducting heat. We got radiation up there bombarding us with waves or photons, however you want to think about it. And we absorb or reflect. We can reflect some of those. And then we're going to have convection. And convection is energy transfer between a solid surface and an adjacent gas. So it's like when you burn your finger, you go, well, with a mask, it probably doesn't work. But, if you take your mask off, you can, blow some cool air across your burning finger. And that's a convective situation. Lots of convection out there. When the wind blows up against the side of the building, that's convection. It could be a cold wind in the wintertime or a hot wind in the summertime, whatever. So energy transfer, solid surface and an adjacent gas, and then it could be a gas or it could be a liquid. Applies to like water, using cooling water to blow over something. By the combined effects of conduction and bulk flow within the gas or liquid. So convection is pretty complicated. When you get down into that, your fluid mechanics, you've got your boundary layer that gets established. If I have a fan blowing across this table, I could have a heater under there, and I could be blowing heat off of the top of the table. I get a fan over here, and I establish this boundary layer, and so I've got some the molecules touching the table. We say it's a no-slip condition. So we say those molecules are stationary. So they're actually conducting heat from that surface at that first layer, but then it makes a molecule hot and it blows away because it's a gas or a liquid, and you're pumping it or blowing it across that thing. So we actually, convection is pretty complicated. You've got some conduction aspects to it and convection, bulk motion of the fluid. Do you stir it or is it just sitting there? Natural convection, the only thing that moves fluid or stuff is the density difference. Or you can have a pump or a fan that blows stuff across there, which will drastically increase your heat transfer rate. So convection is deceptively simple when you see the equation here. The expression is Newton's law of cooling. Old Newton shows up again. Here's an example. Say we've got a transistor or some kind of a computer chip. It has some it's processing stuff in there, so it's generating heat. So that TB, that surface temperature goes up. We got to keep it from destroying itself. So you got a fan on your computer that blows air across the chips and all to carry that heat away, right? Well, So that's a convective situation, that cooling air blowing across that solid surface. And there's the equation. Q dot, again, it's a rate as told by the dot. H is the convective heat transfer coefficient. A is the area of contact between the fluid and the solid. And TB is the boundary temperature down there on the solid, and TF. TF is the bulk. If you get away from this thing, so just a little bit upstream, away from this thing, what's the bulk fluid temperature that you're using to cool it with? So if you're doing that in this room, like, I don't know, I don't think my computer's run, I don't know, it's probably, maybe it is, I don't know, little bitty fan if it is. But so it would be the temperature, the bulk temperature would be the temperature out here, and that would be then blown through the computer, and TB is the temperature, obviously, of the chip that it's trying to cool off. So it looks pretty simple. I had an instructor in heat transfer for a convection course one time, and he laughed, and he said, yeah, this looks simple. We take all of our ignorance and we put it into the H. H is really pretty complicated, and there's lots of, that's where the mathematics really kicks in. There's correlations where you can calculate an appropriate H value based on the type of fluid, whether it's vertical, horizontal, if it's forced or free convection, all that. You've got multiple correlations out there that you go to in order to estimate that H. Because the A and the two temperatures are pretty simple, but the H is where the rubber meets the road. Yes, sir? Now there's correlations. Well, I mean, you can find tables for it, but I mean, H's are tough because, I mean, just a difference in surface roughness or something, or if you change it, you know, like if you do a correlation and you've got a very well-defined fluid velocity profile over that surface. But then in your case where you're trying to do this calculation, you get the air is coming through a case and all this sort of thing, and the velocity profile gets all chopped up. So that H that you calculate from that nice velocity profile may not be very close to the H you actually have. So, I mean, you can find typical values in tables, and you can find these correlations where you go in and you have to put in the density and the velocity and all this stuff, and then you can calculate an H from that correlation. How good is it? I don't know. I mean, if it's something really important, what you do is you do your calculations, and then you do some testing, because you may find 4 or 5 different correlations that could potentially apply. And you go, well, this one gives a number, this one gives 2.5, this one gives 6, this one gives 9, and this one gives 12. Well, crap, I get a big difference in numbers, you know, with that much variation, which is quite possible out of correlations. Well, which one works for me in my situation? You better go take some measurements and see which one you think is going to give you the best result. Okay, so A, area of the transistor surface. H is the empirical parameter called the convection or convective heat transfer coefficient. I guess there are some theoretical correlations out there as well. Most of them, I think, go back to experimental setups. Okay, so that's the heat transfer intro that you get. And we don't, you know, mostly in this class, if there's heat transfer, it's real simple to calculate, or it's given to you. A heat transfer rate or a heat transfer amount, that sort of thing. And then you can use that in your energy balance. Okay, so let's look at cycles. And let's see, I'll do a time check here. How are we doing? 10 o'clock, okay. Thermodynamic cycle is a sequence of processes that begins and ends at the same state. So, you know, and examples are air conditioning systems, heat pumps, power cycles, all that sort of thing. So it's like, oh, I don't know, say a Rankine cycle power plant, you know. say if you look at the working fluid, the water, say it's liquid, it gets vaporized into steam, it goes through a turbine, it gets vaporized into steam at high pressure, it goes through a turbine to low pressure, it comes out, it's still mostly steam, it gets condensed, and then it gets pumped back, and it comes back to the same point. Exactly same condition at which it went into the boiler, and that working fluid keeps going through those 4 processes all day long, and the net result is we make electricity out of the cycle because that turbine is turning a generator. Okay, so when we say cycle, you know, in thermo, a lot of these words are like code words. You see cycle, you immediately think, starts and ends at the same point. And that's why you know, when you first come in here, you just don't know that because you haven't run into it. But that's kind of what you're going to see. Thermodynamic cycle, sequence of process, and it can be any number of processes. It's completely general in nature, but that working fluid is going to come back to the same point after it executes one path through the cycle, goes through all of the different processes, however many they are, and comes back to the same point. That's the start and the end of the cycle. Examples include power cycles, Rankine cycle, Otto cycle, that, you know, your automobile engine is an Otto cycle, diesel cycles, similar to the Otto cycle, but no spark plug. Brayton cycle for gas turbine operations, lots of different power cycles are out there that develop a net energy transfer by work in the form of electricity using an energy input by heat transfer, typically from hot combustion gas. It doesn't have to be combustion. A nuclear power plant, what's nuclear about it is that's the heat source. You got this controlled nuclear reaction that produces heat. The heat goes into the water, makes steam, and from that point, once you get the heat into the water, it doesn't matter if it's coal, natural gas. It could be solar. They have solar power plants. You know, they have the tower in the center, and they have all the mirrors on heliostats that track around and focus the sun's rays up there on top. It gets really, really hot, and basically they circulate water through that, and it makes steam. Once you get the steam, you're off. I mean, it's the same cycle pretty much. So it's just whatever the heat source is that allows us to vaporize something that we can put through a turbine. Okay. Refrigeration cycles. We all like to stay comfortable. So that refrigeration cycle, like in this room, we're generating heat. You're putting off heat. Lights are putting off heat. Computers put off heat. Projectors put off heat. So we got energy here, and we want to pump that energy outside. Well, guess what? It's cooler in here than it is outside. So, you know, I can't just whistle and say, hey, energy, go out there. You know, it don't listen. You know? I got to be careful. I would make jokes, but I got to be careful. So I'm going to be on my best behavior today. You just can't get it to do what you want to. You can't get that heat to go from a low temperature to a high temperature outside without some sort of a cycle that makes it go there. Okay. And there are different types of refrigeration cycles, most of which are driven by a compressor and use electrical input. They could be driven by a turbine. You know, you can put a steam turbine on a water chiller, make cold water, and then do air conditioning with that. Vanderbilt has a setup like that. So we might mention that a little bit as we go forward. And then a heat pump. A heat pump is like in the wintertime, we want to stay warm in here. Say we want to stay at 70 degrees in here, and it's 20 degrees outside, but we want to pump heat from outside at 20 degrees into here at 70 degrees. Well, that's a pretty good trick. You know, again, you can't just whistle and say, hey, energy, come in here. You're 20, you get a little colder out there and move some of that heat in here so I can stay warm. That's basically what a heat pump's doing. So we'll look at all of these. We look at these in layers. We kind of get some general concepts here, and then we'll go back and we'll put all of the processes in later. Okay, so this is how we can draw a power cycle. Okay, so this is one of these diagrams where energy transfers, work energy transfers, are positive in the direction of the arrow. So we've taught you this sign convention, and now we want you to put it on hold for these diagrams. Don't ask me, I don't write the books. It's just what they do. So basically, but what that diagram is saying, we've got some hot object. It could be combustion gases. You know, we're burning natural gas or coal or whatever. And we get heat out of there, and we're going to transfer that heat into our system at some, and that hot body would typically is at some temperature we call TH. We transfer an amount in, and that's an amount, Qn, certain amount of energy. And then we're going to reject a portion of that heat to a cold body, because we'll see from the second law requires that. We can't have 100% conversion of that Qn, that hot, the energy coming in at the high temperature. We can't get 100% conversion into work. So we have to reject some heat to the cold body, which is typically a lake or the air, the atmosphere, some large heat sink, we call it, where we can dump that heat. And then the cycle work is simply the difference between Q in minus Q out. So these diagrams are pretty simple. Chapter two is your friend. It's all pretty straightforward. Energy transfers by heat and work shown in the figure are each positive in the direction of the accompanying arrow. This convention is commonly used for analysis of thermodynamic cycles. So we'll use that on the refrigeration cycle and the heat pump as well. So W cycle, now notice that's not a dot. If it's not a dot, it's an amount. You just have to keep drilling that into your head. If there's a dot, it's a rate. It's an instantaneous rate. If there's no dot, it's an amount that occurred over some period of time. Is the net energy transfer by work, net, from the system per cycle of operation. So in some cases, we may have more than one work interaction in a cycle. You know, you may have pump work, and you may have turbine work, and you may have different types of work. So notice this is the net. When I take all of the work interactions into consideration, this is the net. And coming out, I'm taking as positive. Qn, heat transfer of energy to the system per cycle from the hot body, drawn from hot gases of combustion or solar radiation or other radiation, nuclear radiation or whatever, some heat source. It could be geothermal, you know. Old Yeller blows hot water and you tap a little bit of that, put it into your heat engine, and you get some electricity out, whatever. Well, that's Old Faithful, not Old Yeller, right? Old Yeller's a dog. Cancel Old Yeller. That wouldn't work very well. I don't want to have the animal rights people after me. And Q out is the heat transfer of energy from the system per cycle to the cold body, discharge, atmosphere, lake, river, whatever. Now I will say, the colder the body you can dump that to, the better efficiency we'll wind up getting out of the cycle when we actually get to the cycle analysis. So some power plants dump to the atmosphere, but they really try to build a power plant like in Kingston. The plant, as you go to Knoxville, you see it, it's built on Watts Bar Lake. Watts Bar Lake is far cooler than the atmosphere in the summertime, right? It might be 90 degrees in the air. That lake is 60, 65, whatever. And so you get better efficiency because you can cool with lake water instead of atmospheric air. It's also good for the old retired guys, right? Because you know where they go fishing in the wintertime? Right at where the heat is dumped out of the power plant. Because when it's cold outside, that's where all the fish go. So and if there's a power plant around in the wintertime, all the old guys with their fishing boats are sitting down there, you know, right where that heat's coming out, and they're busting those bass or whatever. Okay. Okay, applying the closed system energy balance to each cycle of operation. Delta E, E2 minus E1 is equal to what? The net heat minus the net work for the cycle. But the cycle starts and ends at the same point. So it's like E1 minus E1. Well, E1 minus E1 is 0 all day long. So what that says is that the work out of the cycle is equal to the net heat. So net work is equal to net heat for a cycle. Okay? In other words, net energy transfer by work from the system equals net energy transfer by heat to the system, each per cycle of operation. So this is all fundamental stuff that you need to make sure that you got. Okay, then the performance of a system undergoing a power cycle is evaluated on the basis in terms of the extent to which energy added by Qn is converted to a net work output. So in other words, it's a typical efficiency. The desired output divided by the costly input. Well, the costly input was the fuel that we burned to get the heat to put in the cycle. Okay? So that's Qn is the costly input, and the desired output is obviously the work. So that's our definition of efficiency. And we call it a thermal efficiency, because this is a thermal cycle. Okay? But we also know that the net cycle work is equal to the net heat. So W cycle has to be equal to Qn minus Q out. So just do that substitution, and then you can do a little simplification. You got Qn over Qn minus Q out over Qn, and so you get equation 243. Okay? Questions? Okay. Now, I will email this out again because, whoops, oh, just a second. I've added a couple slides. I thought it was next, but I got one more here, so I'll do this one. Using the second law of thermal in chapter 5, we'll show that the value of thermal efficiency, it must be less than 1. And that was my comment about you have to reject some heat from the cycle, and that makes that efficiency less than 1. So we'll see that, but that's a requirement. Oh, okay, we got a little example here. System undergoes power cycle while receiving 1,000 kilojoules of heat transfer from hot combustion gases at a temperature of 500 Kelvin, discharging 600 kilojoules of heat transfer to the atmosphere at 300. Right now, we're not doing anything with those temperatures, but it's just to give you some numbers to look at. Taking the combustion gases to the atmosphere as hot and cold bodies, respectively, determine the work and the thermal efficiency. And so, well, these problems are real nice. They're easy. I mean, you know, what the net work is the net heat. I got 1,000 in, 600 out. Guess what? I got 400 kilojoules of work. Pretty simple. And then I got a 40% efficiency because I got 40% of it out in work. I had to put 1,000 in, 40%. So that's pretty straightforward. Okay, and this is what I stuck in. I just went out and pulled a simple diagram. But this is what's inside the box. Okay, and see, so you've got Q in up here on top, and you got Q out over here, and you got your net work Well, so your network, you actually have, here you have two work interactions. I've got turbine work coming out here, and I've got a little bit of pump work going in over here. So the network here is the turbine work minus the pump work. So there you've got two work interactions that you would have to take into consideration. But so you see how you get this, where's the picture? You get that little picture, but so you see the Q in, where that actually fits in the cycle, that's in the boiler, and the Q out, that's in the condenser, because when that steam comes out of that turbine, I mean, all that steam is pure. We purified that water and cleaned it up and put chemicals in it, and we can't afford to throw it away. And the only way to get back in the boiler is you have to condense it, because you can't pump it as a vapor. And so then you take that lake water and you condense it to a liquid, and then you can pump it back to the boiler. So that's what's going on there. So that cooling water is probably lake water. And that flow comes in and it takes that heat with it. So anyway, that's pretty simple. 16. Okay. Okay, refrigeration. So now we've got our same little setup, but the hot body, cold body, and what's in the system is going to change. So for a refrigeration cycle, the cold body is the room. We want to keep it cool. And the hot body is out there. Assume it's 90, 95 degrees. And so we run the cycle because we want to pull that Q in out of the room, and we want to stuff it outside, because that's the only place we got to put it, one way or the other. But in order to do this, we have to have some work input to make this cycle operate, okay? The energy transfers are each positive in the direction of the arrows. Again, we're going to say that. W cycle, net energy transfer by work, same thing, per cycle of operation, typically electricity. QN, heat transfer of energy to the system per cycle from the cold body, drawn from, this could be a refrigerator or a freezer. Okay, so this brings up the classic question. Let's say your air conditioner in your house is not working real well. Your house is kind of like 80, 78, you know, it's just not quite comfortable. So your significant other, that's this great idea. Why don't we just open the door on the refrigerator, right? So you open the door on the refrigerator, and some of that cool air comes out into the kitchen, and you let it sit there for a while. Does the kitchen get warmer or colder? Why? Yeah, because it's true. You are pulling a little bit of heat out of that space, but you have to reject all of that heat, plus you have to reject the compressor work. And where does it go? It goes out the back of the refrigerator into the kitchen. So you open the door on the refrigerator. Now, if you stand right there, or if you crawl in a little bit, okay, locally you might be better, but in general, you're moving that heat, and you're putting in the work of the compressor, so the space is going to warm up. So unfortunately, that's not viable. Now, if you took that condensing coil and dumped that heat outside, then it would work. See, then that's what your air conditioner is doing. But because it's all dumped in the kitchen, you're just going to heat it up. Okay, Q out, heat transfer of energy from the system per cycle to the hot body. Discharge to the space surrounding the refrigerator, for instance. Okay, so again, it's a cycle. So delta E has to be 0 for a cycle, because it starts at 1, it comes all the way back around to 1 again. Delta E, E1 minus E1 is 0. So this is the same. Work of the cycle is equal to Q out minus Q in. Or let me see, is that what we had before? Yeah, I think it is. Anyway, I mean, it just refers to this diagram. In other words, net energy transfer by work to the system equals net energy transfer by heat from the system per cycle of operation. Okay, and so now this is our efficiency. But we don't call it an efficiency because I think I mentioned the other day, we call this a coefficient of performance. But if you look at it, it's the desired effect divided by the costly input. Well, I got news, that's an efficiency. But because it's a number greater than 1, we don't call it that. We change the number. So this is the old COP. And you need to know, that's one of those things you ought to memorize. COP is basically the efficiency with which an air conditioning system or a heat pump will get a similar definition, not exactly the same for the heat pump. But for a refrigerator or for an air conditioning system, we run the system to get Q in, right? Because Q in comes in from the cold body. The cold body is the room or the food compartment that we want to keep cold. So Q in is the reason for running the system. And W cycle is what we have to pay. That's the electricity it takes to run the compressor. So that's the costly energy input. Okay? Coefficient of performance, refrigeration. And this book uses a beta for refrigeration when you're in cooling mode. And again, W work of the cycle is Q out minus Q in. So you can substitute that in, and no other simplifications on that. And there is a nifty little picture. Again, I pulled that off the internet today. And so, you know, so how is it that we can transfer this heat from this cool room to the hot outdoors? Well, we have a working fluid. We have a refrigerant. So basically what we do is at the top of this thing, when I come out of this metering or expansion valve, that's a pressure drop. This refrigerant gets really cold. It's like 38 degrees. That working fluid's 30, 37, 38, 39 degrees. Well, if you're 38 degrees, a 75-degree room looks pretty darn hot, right? And so you put that cold refrigerant through that coil, and all those little kilojoules or BTUs or whatever you want to think, they go hopping from the air through the coil into the refrigerant. Okay? So then all that heat goes into the refrigerant. And we'll find out that basically it's going to boil it away, you know, like boiling water on the stove, but it's going to boil that refrigerant from a liquid into a vapor. And so that energy is inside that vapor, and it's going to go into that compressor. It's already a vapor. It's low pressure. That compressor, boom, 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 heats it up, puts a bunch of energy into it, right? It's hot. How hot's the refrigerant coming out of a compressor? I don't know, depends on the refrigerant, 150, 180, 180 degrees. Well, when you're 180 degrees, that 95-degree air out there looks pretty good, looks pretty cool. So then I can dump that heat, the heat of compression, plus the heat that I picked up from the house, I can dump it all outside because I'm 180 and it's only 95. So all that heat just leaps out. And so the air coming out of that condenser instead of 95 is 98, 99, 100. Who cares? It's still cool compared to 180-degree refrigerant. So that's how I dump it outside. And in order to make that cycle work, guess what? I got to put electricity in it. I got to turn that compressor. So That's how we do it. Now notice this thing called reversing valves. So note that for a second. Notice the path. We come out of the indoor coil and we go into the inlet of the compressor. We come out of the compressor, the hot gas, and we go to the outside coil, right? That's what we just discussed. Just file that away. Okay, let's look at a heat pump. Well, what's the purpose of running a heat pump? It's to stay warm in here, okay? So now the room is the hot body because I'm going to have to pump heat into this place because it's cold outside, okay? So the room is the hot body. The cold body is out there, and I've got a cycle, and I'm going to have to put work in it because I can't get that energy out there to just want to come back in here unless I force it with a cycle. And the cycle is all what's inside the box, which is the system. So it's similar, but the reason, say over here, the purpose was, the desired effect was Qin to keep the space cold. Here, the desired effect is Q out to keep the space warm. So the space is changing location between a heat pump and a refrigerator or an air conditioner. Okay. Now the focus is on Q out, which is the heat transfer of energy from the system per cycle to the hot body, such as a living space or dwelling. Qn, heat transfer of energy to the system, which is typically drawn, it could be the ground, it could be a lake, or it could be the air, but it's typically outside someplace where it's already cold, but we can still pull heat out of it and make it colder. Okay, so as before, W cycle, net energy transfer by work to the system per cycle, usually provided in the form of electricity. And so as for the refrigeration, so the energy balance, because it's a cycle, E1 minus E1 is 0, so the energy term drops out after we execute a full cycle. And so we get the net cycle work is the difference in heat. Net work is net heat. Okay. Now, this is the efficiency. So this is the coefficient of performance. And we use a gamma, a lowercase gamma for this. And it is the desired output, which is the heat, the heat from the cycle going to the space is why we run it, to keep the space warm. And the costly input is the cycle work. So this is the coefficient of cycle of the heat pump. Now notice for the refrigeration system, that was Qin, and that was beta. So gamma is for the heat pump, and it's Q out. So it's almost the same thing, but not quite. And so, and then you can put in the definition of work in terms of Q out minus Q in. And so that's for the heat pump. Okay, so we got a little example on this one. System undergoes a heat pump cycle while discharging 900 kilojoules of heat transfer to a dwelling at 20 degrees C, receiving 600 kilojoules by heat transfer from the outside air at 5, taking the dwelling and outside air as hot and cold bodies respectively, determine for the cycle the net work and the coefficient performance. Well, you know, net work is net heat, so that's going to be what, 900 minus 600. You can see that coming. That's 300. And so then the coefficient of performance is the desired, which is 900, divided by the 300, which is the work. So it's 3. There you go. So, and there, now, our reversing valve has rotated, right? And now, let's see. So look, the flow's in the opposite direction across the expansion valve, right? It was going the other way before. And so now Now we've got our cold, and you can tell, you know, the hot is red and the cold is blue. So that on the low pressure side of that expansion valve, in this case, in the heat pump mode, that may be 0. That may be minus 10 Fahrenheit. That's minus 10. It's 20 degrees outside. Guess what? When you're minus 10, 20 looks pretty good as far as getting warm, you know? So that really cold refrigerant goes through that outdoor coil, and you blow that outdoor air across it at 20, and guess what? You pull heat. You cool down that 20-degree air. You cool it down to 15, and that heat goes into that refrigerant, okay? And so that refrigerant boils away. See, it has to boil because you're going to put it in a compressor, and that compressor is not going to like liquid. You'll tear up the compressor if you slug it with any liquid droplets. So you know this thing is engineered so that coming out of that outdoor coil in heat pump mode, you're all vapor, okay? Because you're going to put that in that compressor, and guess what? When it comes out of that compressor, it's going to be pretty warm. It's going to be, this is colder outside, so maybe it's 110, 120. But that's enough to heat your house. So then you come out of that compressor, it's red, and it goes through that coil. Now that's the coil inside your house, and you blow air across it, and you take heat out of the refrigerant, and you heat your house. So basically it's the same device, and all we've done is change that reversing valve position. Because, you know, anybody have a heat pump at home or anything? It's got on the thermostat, you got heat and cool. Well, when you change, you're positioning that thermostat valve, that reversing valve. And it adjusts pressures in the system a little bit. But basically, that's what you're doing. Yes, sir?
So, to get like a certain temperature in your house, is it the compressor that would, like, say if you want a lower temperature, that would like work at a lower rate? Fans going through the condensers below.
Well,
exactly. Is it a combination of both maybe to get a certain temperature?
these days they can do all kinds of things. It kind of depends on how expensive. You know, they can put variable speed fans on things so that you can modulate the fan speed, right, so they can control the refrigeration system a little bit independently. And so, you know, where the optimization is on that right now, you know, I'm not sure. Like on my systems that are cheap, the fan just clicks on and clicks off. And when the fan clicks off, the compressor clicks off. And so they just kind of come on and off together. But these days, depending on the sophistication that you want to buy and how much you want to pay for it, I think you can get much better control. Because, you know, if you're going to click that thermostat on and off, then you're going to have a band, right? Say you set it on 75, well, when it gets up to 76 or 76 and a half, it clicks off, and then it coasts down to maybe 73 and a half or 74, and it just keeps working up and down in that band. If you do it with a speed control or something, then you can pretty much have a constant set point. All right. Well, let's see. We got 15 minutes, don't we? I sometimes lose track of time here, I think. Yeah, that's the end of this. So I thought what we do is look at some of these example problem solutions, just a couple of them. This 57 is a pretty good problem. So I thought we might look at that. And this is one, and I'll be emailing this stuff out to you. But so we've got a gas and a piston cylinder here, and it's undergoing a cycle. So it's going all the way around, coming back to the same point. The first process is constant pressure, and the pressure is 1.4 bar. And the initial volume is 0.028 meters cubed, and we're given the work interaction, okay? And so we can move up and down on this. So let's just look at, so 1 to 2 is 1 to 2, constant pressure. So we got this nice rectangular area that's going to represent the work on a PV diagram for us. So that's, but they've already given us the work. But that's that area from 1 to 2 down to the volume axis represents that work quantity. That's that integral done for you. Let's see. 2 to 3 is compression. It's a polytropic compression with PV and volume just to the first power is constant. And they're also saying that internal energy, U3 is equal to U2. And 3.1 is constant volume, and U1 minus U3 is a minus 26.4. Okay, so you know, and this is this structure that they recommend for problems, which, I mean, it is good. It's a little bit laborious to write out all this stuff, but anyway. So now gas undergoes a cycle consisting of 3 processes. Sketch, well, find, we sketch on a PV diagram and determine the net work for the cycle and the heat transfer for process 1, 2. And so schematic and given. So he's just restating, draws a picture of a piston cylinder, restates the information that we're given. Engineering model. Gas is a closed system, so we don't have any mass crossing a boundary. Kinetic potential energy effects are negligible, and that's because this piston cylinder is not sitting on the back of a truck. It's not going down the interstate. It's not going up or down Monterey Mountain. So it's just sitting there, and the piston is moving back and forth. So yes, there's kinetic and potential energy changes in the molecules, but that is described by the internal energy term. Okay. And this is not always. We'll have some problems that may have the whole thing moving, but this is pretty typical. And there's our PV diagram. Okay. Let's see. So analysis 1, he says, work 1 to 2 is greater than 0. Now this is back to the actual sign convention on work. So positive work takes energy out of the system, okay? So E2 minus E1, if that's positive, then, is that right? It's taking energy out of the system. Yeah, okay. So that tells you that V2 has to be greater than V1. So the question is, you know, when you first start drawing this, you don't know whether the process 1 to 2 volume gets bigger or smaller, but it's the sign convention on work that tells you that. Okay, so once you have that, then this is just kind of the way this polytropic process gets drawn. Probably not exact, but it's pretty close. And then this is constant volume, so it comes straight back down. And it's a cycle, so it has to come back from 3, it has to come back to 1, so it starts all over again. Okay, so net work for the cycle, well, that's work interaction 1 to 2 plus 2 to 3 plus 3 to 1, but you know that 3 to 1 has to be 0. Why do you know that 3 to 1 has to be 0 for work? What's the area under the curve on a PV diagram? Because work for a compression is the integral of P dV. Well, what's dV? Zippo. So there's no work. Okay. So that's how you know that. Okay, so he throws that away. And work 1 to 2 is given. So we just need to calculate work 2 to 3. Well, so there's our integral from V2 to V3 of P dV. And so it's all these polytropic deals are the same. It's just the exponent changes. So let's see, where's the relation is right here. PV is equal to a constant. So you want to solve for P in terms of volume. And so that's what he's done and substituted in. So P is equal to whatever that constant is divided by V times dV. Well, that constant is P1 V1 or P2 V2, whatever state that you know both, that evaluates the constant, because the equation says that pressure times volume at any point is constant. So he's making that substitution, and then he does the integration, and you get V3 over V2, but V3 and V1 are equal because that's a constant volume, so he just substitutes in. Okay, so there you go. So we can evaluate that. Let's see. We need to know V2, but so this is for the constant pressure process for the work from 1 to 2, integral V1 to V2, PdV. P is constant, integrates into V2 minus V1. So you can solve this for V2. And, you know, to me, conceptually, this is pretty easy, but just got to be careful with the units. Those units are awful, I think. But anyway, just be careful. You're just going to have to learn how to juggle the units. You will have those conversion, you know, on a test. It's open book, so you'll have your conversion factors. But you're going to be time pressed. I mean, I'll just tell you, you're going to be time pressed on the test. So you're not going to be able to go teach yourself how to do units on a test. If you're not already quick at it, you won't get through the test, you know, or you'll get wrong answers, whichever. All right, so this gives us V2, 0.103 meters cubed. And then we can evaluate this expression up here for the work 2 to 3. So crunching the numbers, converting the units. We get minus 18.78 kilojoules. And so then the net work for the cycle is the first process 1 to 2, 2 to 3, and 3 to 1 is 0. So it comes out minus 8.28 kilojoules. And then the last part, we're just going to do the energy balance for process 1 to 2. So there's the whole energy balance for control mass. Change of kinetic energy, 0. It's not on a flatbed truck. It's not moving. Potential energy, it's not changing the whole system, not changing elevation. They go away. They gave us the change in internal energy, and let's see. No, I take it back. Let's see. So Q is solving this with U2 is equal to U3. So we know that, and bingo, we just plug in. We know the work, and so we get 36.9 kilojoules. Questions? Okay. All right. I think that's probably enough of this for now. I will email out you all of these solutions, and we will continue on. We'll, I guess, crack into chapter 3 on Thursday. So I hope you guys have a great rest of the day.